Okay. Okay. Hello everyone. The work I will present today is spatial temporal embodied carbon model for the embodied carbon counting of computer system. I'm Zhang Xiaoyang, and I have two collaborators, Yang Yijie and my supervisor, Prof. Then the embodied carbon of computer hardware is a carbon released in manufacturing. In a chain of semiconductor, the raw material is sand, which is processed into silicon and then wafer. And from wafer to chip, there are also many processes, such as oxidation, photolithography, and so on. The carbon in the first stage is mainly from raw material, and the carbon in the oxidation is mainly from chemical gas. And the carbon in the photolithography is mainly from electricity. Overall, the carbon is mainly from three components: raw material, chemical gas, and electricity. There are two existing methods to account the embodied carbon of computer system. The first is LCA-based. It directly uses the values in LCA reports. The second is ACT model, which estimates the embodied carbon of key hardware components. It estimates processors by modeling the carbon in the three components as we discussed before. For example, the embodied carbon of 28 nanometer CPU is 1080, which is calculated based on the three components. The first is electricity consumed and the raw material and chemical gas. Will ACT estimate memory and storage also by directly using the values in LCA reports. We observe that they all estimate the carbon of product class, such as 28 nanometer CPU. However, the carbon of its product instance, such as made in summer in Taiwan or in winter in Ireland, can differ. For example, as a class of 28 nanometer CPU, the instance in this class may be manufactured in Taiwan or in Ireland. The power grid of Taiwan has more brown energy, resulting in the high carbon intensity of electricity. So the instance manufactured in Taiwan has a high embodied carbon. Well, the grid of Ireland has more green energy, resulting in low carbon intensity. So the instance manufactured in Ireland has a smaller carbon. The manufacturing time can also affect the embodied carbon. For example, the instance may be manufactured in winter or in summer. The grid in winter has less green solar energy, resulting in the high carbon intensity. So the instance has a larger embodied carbon. Well, the grid in summer has more solar green energy, resulting in the lower carbon intensity. So the instance manufactured in summer has a smaller embodied carbon. And to solve the problem, we propose spatial temporal embodied carbon models by combining ACT model and the carbon intensity model. We call them stack models. Our evaluations show the significant difference between the stack models and the ACT model. For example, the difference of 7 nanometer CPU can be 13.69%. And we also use stack model to account the embodied carbon of two computer applications, LM carbon for LM training and the carbon mini for LM inference. And we can find the difference of LM carbon is 6.35%. which is smaller than that of carbon mini, 32.26%. This is because carbon mini use ordinary hardware with great spatial temporal choices in manufacturing, while the hardware for carbon is more restricted. Here is details of stack models, which is based on ACT model and carbon intensity model. Through the carbon intensity model, CI, we can get the carbon emission rate of electricity at the manufacturing time T and the location S. Then the stack can be calculated. For example, the carbon of processors can be calculated by a CI with location S and the time T, multiplying the EPS, which is the electricity consumed per size, and then plus this GPS, which is means carbon from gas, from chemical gas, and then plus this MPS, which means that the materials per size. As for the memory and storage, the stack can also calculate the carbon from electricities as this read block shows, which is with spatial temporal property, and the carbon independent of electricity as the block shows, which is without spatial temporal property. Second models need finer granularity carbon data, but it is not always available in each region. For example, daily data is not available in China. Actually, there are many regions that have no finer data, as this green block shows in this map. Additionally, we observe that different applications may need carbon data at different granularities. For example, manufacturers that regular purchase for their assembly lines may care the year level, and the consumers with flexible may care the finer granularity, such as seasonal level or even day level. So we propose a set of stack models according to different spatial and temporal granularities. Along the spatial dimension, there are country zone and global level. Along the temporal dimension, there are day, season, and year level. We made an effort to collect data in order to study stack CD, CS, and ZY. The existing model can treat it as stack GY, which is in global and year level. And the current data cannot support us in studying this purple 4. We try our best to collect data from a variety of sources, such as public data supplied by power grids, research papers, industry research reports, and manufacturer reports. And we open source all data and codes. Here is the details of evaluations. First, all stack models have a significant difference with ACT model. For example, the difference of 7 nanometer CPU can be 13.69%. Actually, additionally, finer granularity can bring more dynamics. For example, the stack CD has more dynamics than CS and ZY, as this read block shows. Here is a case study. In 2022, Storm Malik hit Ireland. Let's see what happened in the embodied carbon counting during the storm. When the Storm Malik arrives, the wind power grows fast, and the embodied carbon decreases repeatedly, and reaching a minimum at 5 p.m. The reason for this decay is the wind power increased repeatedly, resulting in a low carbon intensity of electricity. Here we recalculate the embodied carbon of LLM carbon and carbon mini use our second model. As we talked before, the difference is also significant. And LM Carbon use high-end and specific hardware such as V100 GPU and the sensing 20 nanometer SSD with fewer manufacturing choice. So the difference of LM Carbon is smaller than that of Carbon Mini. Here is the conclusion. First, we observe that for the same product class of computer hardware, the carbon of its instance can differ. And then we present new stack models by extending the embodied carbon model in spatial and temporal dimension. And we open source the data and codes. And at last, we evaluate the stack with a state-of-art model. And we also apply the stack for the embodied carbon for two computer applications, and the results show that significant difference can exist. Okay, that's all. Thank you.